Yeah, so today we'll discuss propagation loss or attenuation of the optical signal in an optical fiber. It's important to know where this loss comes from. Although optical fibers have extremely low loss compared to any other means of transmission, but you should still know where the limits are so that people are still trying to improve things, right? So usually we measure the loss in units of dB per kilometer, right? So just to remind you, so dB is basically some ratio, right? So when we are measuring loss, it's basically the ratio of the input power to the output power. So we convert that to decibels like that, right? And then if we divide by the length, so the optical fiber has some length L over which we are sending the signal, then basically this is the loss in dB per kilometer, right? So you know, as like if you have a signal and it's propagating, usually the amplitude of this signal goes down, right, due to losses, like could be absorption or scattering or whatever, right? And typically the power goes down in a medium like this, right? So fraction of the power is lost per unit length, right? And this is the loss coefficient for the medium. So I'll put a subscript n here to distinguish from here. So these are in natural units, right? So this alpha has units of per length, right? So for example, per kilometer, right? And this is the usual Beer's law or Beer-Lambert law of loss, the power loss in an electromagnetic wave in a lossy medium, right? So you can, I mean, you know that. So if you just integrate this equation, then the power after a length L is the initial power times this exponential factor. So you can try to compute this alpha in dB per kilometer in terms of this alpha sub n, right, which is in per length. So if you do that, these two quantities are related like so basically you can plug expression for PL into here, right, PR. So relation is something like, so once you take the log of E and etc., this goes something like that. Okay, so this loss coefficient is a function of wavelength. If you take any material, usually it's a function of wavelength, right? And so same for optical fibers. So if you plot this alpha as a function of wavelength, so typically the lowest loss for glass, pure glass, like which is what optical fibers are made out of, that occurs in the near infrared region. So the wavelength on the x-axis is in micron. And if you plot the loss on the y-axis, so we're plotting in a log scale. Okay, so there are these fundamental limits which we discussed. So this is dotted line here. Okay, so if you take any typical optical fiber, the loss as a function of wavelength looks somewhat like this. Okay, so um, so what are these two lines? These dotted lines that I've drawn here. So fundamentally, again, like if you take a pure material, some dielectric like glass, and then so the band gap is very large, right? Some 9 electron volts or something. So that corresponds to a wavelength which is into the UV, like some. So the band gap wavelength corresponds to about 200 nanometers or something. So you are way down here. So all these wavelengths are less than the band gap. Okay, so there should be no absorption loss because the energy of the photon is not enough to cause a transition, right? But there are other loss mechanisms here, right? So this line is basically what is known as Rayleigh scattering. This dotted line here. Okay, and this dotted line here is basically infrared absorption due to phonons. Which are basically lattice vibrations in the medium. Okay. So Rayleigh scattering is basically due to the fact that so glass is an amorphous medium, right? Which means it doesn't have a crystalline structure, right? It doesn't have a periodic arrangement of atoms. So there are small density variations with position, right? So if you take one position that, if you take some fiber here, so if you take a position here and see what the density, that might be slightly different than some other position here, right? So there are some small density variations with position, and these density variations basically cause scattering of photons, right? So you can imagine, so for example, the refractive index depends on the density, right? So there are very small refractive index variations, right? So these variations are extremely small, like let's say part per million or part per billion, but basically they do cause some small amount of scattering, right? And if you have very long lengths, as we have for optical fibers, these can actually become significant, right? And so Rayleigh scattering fundamentally comes when the size of these variations are much smaller than the wavelength. Okay? So these density variations are occurring over very small lengths, let's say nanometer scale, right? And so they are much smaller than the wavelength. So this Rayleigh scattering scales with wavelength. So this is a fundamental phenomenon, right? So if you have any medium where there are density variations on a scale much smaller than the wavelength, then that medium will have Rayleigh scattering. For example, actually this is the reason that the sky looks blue, right? So when you look up at the sky, in a direction away from the sun, it looks blue, right? But that's not because there is some material in the sky which is radiating blue light or emitting blue light, right? What's happening is basically the sunlight has all colors of the spectrum, it has all wavelengths, and then basically this Rayleigh scattering depends or scales with the wavelength like 1 over lambda to the fourth. Okay, so as you increase the wavelength, the loss goes down, and it goes down significantly, like a fourth power. Right? So, for example, so you have sunlight, right? So it has all wavelengths across the visible spectrum, and so what happens is due to the atoms and molecules and dust particles, etc., in the atmosphere, right? All of those having a size much smaller than the wavelength, they scatter light in all different directions, right? And this scatterings goes like this, right? So lower wavelengths are scattered more, right? So this coefficient is larger for smaller wavelengths. So blue light, which has smaller wavelength, is scattered much more than, for example, red light, right? So that's why when you look up in a direction into the sky, basically what you are seeing is the scattering from the particles in the atmosphere, right? And prominently you see blue because the scattering of blue is much more than other wavelengths, right? Similarly, like during sunset or sunrise, when you look directly towards the sun, it looks reddish, right? And that's again because now what you are seeing is directly the light coming from the sun, right? And the smaller wavelengths are all scattered away from you, right? So the blue, green wavelengths are scattered away from you, and the red is scattered less. So more of red remains in the light coming directly to you from the sun. So that's why during sunrise or sunset, when you look directly at the horizon towards the sun, it looks red. Right, anyway, so the same phenomenon is happening here in optical fibers also. Right, so these constants alpha naught is about 1.7 dB per kilometer at a wavelength lambda naught of 850 nanometer. Okay, so basically if you just had Rayleigh scattering, then if you go towards longer and longer wavelengths, you do better and better. Right? So at the telecom wavelengths, which are the most popular telecom wavelength, which is about 1.55 micron, the Rayleigh scattering coefficient is about 0.15 dB per kilometer. Okay, but then towards higher wavelengths, what happens is another loss mechanism starts showing up, which is this infrared absorption, right? So what's happening here is, so if you take any solid material, right, there are always lattice vibrations due to temperature, right? So these atoms or molecules are jiggling around, right? And basically the quantized versions of them are called phonons, right? And so basically they carry some energy, right? And if the vibration has the energy scale of that matches the photon energy, then basically the photons are coupled to the phonon. Okay, so basically what can happen is like the material can absorb photons and then increase its vibrational energy, right, or the number of phonons. So this phonon induced absorption happens for glass towards longer wavelengths like that. Right? So the resonance for the phonons occurs somewhere here, right, beyond like 2 microns, 3 microns, somewhere there. So basically it's an increasing function of wavelength. So this IR absorption sort of has this kind of form. Okay, so it's an increasing function of wavelength. Okay, so basically you have these two complementary loss mechanisms which are fundamental. Even if you are 100% pure glass with no impurities, defects, anything, you still have these two loss mechanisms. Okay? And you can see that, so this line basically, which is what you will get if you measure loss in a typical optical fiber, is close to these fundamental limits, right? So there are these peaks which show up here, and these are basically due to residual moisture. So these are peaks due to absorption by OH minus ions. Okay, so these are not fundamental. So these are because there is some residual moisture remaining typically in the fiber. Okay. So these peaks occur around 1.4 and like 1.24 micron. Okay, but you can see that, so typically what happens is the minimum loss occurs around a wavelength of 1.55, right? Which is why 1.55 micron is sort of the most popular wavelength which is used. And typically the range of wavelengths between, let's say, 1.5 to 1.6 micron, that's where the loss is minimum. Those wavelengths are used heavily in optical communication because you can send signals over longer distances. So the loss, the total loss at these wavelengths around 1.55 microns. So let's say around 1.5 to 1.6 micron wavelength, the total loss is typically about 0.2 dB per kilometer. Okay, so you can see it's quite close to this Rayleigh scattering limit, right? So basically the technology for making optical fibers has improved over the years, and now basically we are near the theoretical limits, right? So we can't really do much better by improving the technology for the manufacture of fibers. Maybe I'll just briefly mention so how are fibers made, right? So these are really thin. So you have a core and cladding, the total, and then maybe you have some protective jacket surroundings. So the total thickness here is typically like say 100 200 microns, right? And the length, as you know, can go up to kilometers, hundreds of kilometers. So how is this thing done, right? So what you do is you start with a free form which is much bigger, right? So you start with some cylindrical rods, so of let's say millimeter to centimeter size, so much bigger, right? So the techniques for shaping glass are well developed. So you make these big preforms, and then what you do is basically heat them, right? And then you have a thing which basically pulls this. So you heat this preform, and it you know that if you heat glass, it starts sort of melting and flowing, right? So then you basically pull the region where it's melting, and you keep pulling until basically it becomes very, very thin, right? So here you have some like pulling thing which is pulling this fiber. So you have these big fiber draw towers, right, which are like tens of meters tall, and then you have these heating elements, and then basically you draw them into very thin fibers, and then you can like spool them up here. Okay, and so this technique has been perfected sort of over many years to get these ultra pure glass fibers with extremely low loss. Right, so as sort of the internet traffic and demand for data keeps increasing, right, then people are trying to push more and more data through these optical fibers, right? And so one way to do that is to use more wavelength channels. Okay, so you can see here that like for sort of the typical like conventional fibers, like the window is quite small, right? So once you start going towards here shorter wavelengths or longer wavelengths, the loss increases quite steeply. Okay, so this one you can't really do much. This is fundamental, right? But here these peaks are not fundamental, as I said, they are due to residual moisture. So if you could somehow get rid of that also, then like you can suppress these peaks and then go towards shorter wavelengths. Okay, so over let's say last 10-20 years, people have also figured out how to do that. So these big companies which make optical fibers like Corning and Lucent, Alcatel, these companies have figured out how to make what are known as dry fibers, okay, without any moisture. So basically what those fibers look like, the loss coefficient, so now I go from let's say 1250 this lambda in nanometer. Shear loss. So the conventional fibers which have some residual moisture. By the way, that moisture remaining usually is typically very small, like 100 parts per billion or something. Okay, so that's very small amount of moisture, but that still has enough absorption to give those loss. Because we are talking about extremely low loss here, right? We are talking less than a dB per kilometer. So again, if you look at those conventional fibers, so they have a peak at 1.4 micron, right? And then another one here at like 1250 or 1240. So that's how the conventional fiber loss looks like, right? But these dry fibers, basically, they can get rid of the moisture to even larger extent, like less than 1 part per billion. So then basically these peaks go away. So you get something which looks like this. Okay. So these are, let's say, your conventional fibers. And this would be your so-called dry fibers. Okay, so with this, the dry fibers, you can get like sort of loss less than 0.5 dB per kilometer over this entire wavelength range. So from 1.25 to 1.65 micron. Okay, so basically you sort of can use this entire band of wavelengths here. Okay, so you have a lot more wavelength channels available to you to send data simultaneously, and your data rates can really go up. Okay, so nowadays people demonstrate like a terabit per second or more than terabit per second data transmission quite routinely. Okay, and these typically this whole band is divided into different bands. So like this is called C band, this is L band, this is S, I think this is U, and so just like in the microwave spectrum you have these different bands, right? Similarly in the optical communication wavelengths, the ITU, International Telecommunication Union, has described different bands. So the C band is the most popular, right, which is around 1550. But these now other bands are also used to boost data. But to use that, basically you have to use dry fibers, which is sort of a recent technology. Okay, so let's say now, so the fibers, so these, especially these dry fibers, are basically at the fundamental level. Right? You can't really do any better if you are using pure glass. So if you want to do better, then the only way is to somehow, right? So the problem with glass is that towards longer wavelengths, this IR absorption starts coming in, right? The Rayleigh scattering keeps going down, right? So, and that will be true for any material, because Rayleigh scattering is, as I said, sort of a fundamental scattering mechanism which just depends on these very small size scattering particles. So it doesn't depend on the actual composition of the medium. Okay, so if you go to some other materials, then you still have this Rayleigh scattering going down, but this IR absorption actually depends on the lattice vibration and the phonons. So that depends on the composition of the medium. Okay. So one thing that people are trying now are going to so-called fluoride fibers. So fluoride fibers, basically they have fluorine in their composition. Okay. And so people are trying different materials. So basically, the first thing to do is try to dope this flow. Because the technology for glass fibers is developed so well. I mean, why can't you make fibers out of any other materials? Basically, you can't do this. You can't heat them up, melt it, and pull it into thin strands over long lengths, right? That's just we don't know how to do that for other materials. Because glass is soft and it flows, we can do this. So first thing people are trying is what are known as fluoride glasses, right? So basically you take glass and dope it with some fluoride-based materials like zirconium fluoride. There are all kinds of materials people are trying. And basically what that does is that it pushes this IR absorption towards even longer wavelengths. Okay. So basically it starts showing up now beyond, let's say, 5 microns or 10 microns, right? So now you can go towards longer wavelengths where the Rayleigh scattering loss is even smaller. So you can go to 2 microns, 3 microns with these pipes, right? And theoretically they should have even lower loss, so even lower than 0.2 dB per kilometer. So people have theoretically proposed you can go down below 0.1 dB per kilometer. You can maybe even improve an order of magnitude from 0.2, right? So that would be revolutionary. That would mean that, for example, you require a lot less optical amplifiers and repeaters in the way, right? You can lay down much longer fibers, connect much longer distances. So anyway, but this is still sort of ongoing research. Most of the commercial optical network which is laid down is still just this pure glass optical. But anyway, so that's sort of one promising route to go towards even lower losses. Okay. But with glass, basically, we are at the best limit that you can have. The pure glass, silica glass. Okay, so I think that's all I wanted to discuss about propagation loss and attenuation. Any questions on this?
Sir, how dry fiber fabricated?
Sorry?
The dry fibers, how are they
Yeah.
fabricated?
Well, so a lot of that technology is proprietary, so they don't really reveal exactly. But basically, the idea is to somehow like extract all the moisture out of this by drawing. Right. So of course, when you heat and melt it, then you are anyway expelling moisture, right? But there is, as I said, like a small amount left over usually. That's still like less than a part per million or something. But these dry fibers are down to like part per billion. So they do some extra stuff here to extract even more moisture. But because these companies have sort of monopoly over this, they have patents and proprietary information on that, which they don't really reveal actually how exactly they do that. Right? Because telecom operators will have to buy from these. If they make it open, then people can make their own. Right? So.
Okay.
Right, I think, I mean, the trick is basically if you try to heat it up too much, what happens is then this strand, because once it becomes too thin, then it's very fragile, right? And if you try to heat even more to expel more moisture, then there's a chance that you actually start breaking this strand into like droplets or something. Okay, so that's probably like the technical challenge here to master. Yeah. So these companies have figured it out. So I don't know, maybe they share some information on their web pages. You can try to go check it out. Corning, Lucent. Sometimes these are also called like all wave fibers. Because you can use all the wavelengths in this band.
Sir, for the fluoride fibers, as you said, the loss is about 0.1 dB per kilometer. So it is at the wavelength of 1.55 or any other wavelength?
No, longer wavelengths, right? So
Wavelength shift, there is a shift of wavelength to achieve.
yeah, because so as we discussed here, right? So the Rayleigh scattering limit, right? So at 1.55, the Rayleigh scattering limit is 0.15 dB per kilometer, right? And so pure glass fibers are already very close to this, right? So they have 0.2 or maybe some fibers have 0.18, right? And as I said, this Rayleigh scattering is fundamental. It really doesn't depend on what kind of material you have, right? So even if you go to fluoride fibers, you sort of have this limit, right? So now if you want to go lower than that, you have to go to longer wavelengths because then the Rayleigh scattering goes down, right? So now you go towards longer wavelengths here. So you go beyond 2 micron toward 2 to 3 micron somewhere there, right? So then you go down to 0.1 or 0.05 dB per kilometer. Yeah, but then what also you need to do is glass has this IR absorption, so you need to push that out beyond your wavelength range of operation. Right? So that's why you go to this fluoride. So the IR absorption gets shifted out beyond 5 microns. So for the next generation,
But sir, it will also happen for other fibers also, like normal fibers. The Rayleigh scattering will goes down. So what's special about the fluoride fibers?
yeah, so the special is this shifting this IR absorption, right? So this Rayleigh scattering is, let's say, the same for all types of fibers, right? So if I just had Rayleigh scattering, then a simple way to reduce loss is just to move towards longer and longer wavelengths, right? Because the loss goes down with wavelength. But what happens in glass is that beyond like 1.6, 1.7 microns, this IR absorption starts going up really fast, right? So then that takes over. So now if I have some material where this IR absorption is now happening at much longer wavelengths, then I can go towards longer wavelengths and then my loss, if it's determined by Rayleigh scattering, will go down. Right? That's what you're doing.
Sir, thank you.
Yeah, so Rayleigh scattering is fundamental, you can't really do much, right? So as long as you have density variations, so as which will happen if you have an amorphous medium, right? The only way to get rid of this is go to a purely crystalline medium where you don't have any density variations, right? So like a pure crystalline solid, like if you take pure silicon or something, you have a very well-defined arrangement of atoms, right? But then you can't draw them into fibers because you can't melt and heat them, right? As soon as you heat them and try to melt them, they will lose their crystalline structure and right. So if you want to have fibers which are thin and long, then they have to be amorphous materials. And as soon as you go to amorphous materials, you will have Rayleigh scattering. There's no way to avoid it.
Hello, sir.
Yeah.
So how do they make these fibers so that they will work for a particular wavelength range? Is that by controlling the coherent cladding size of that fiber?
But so this what we discuss here is it doesn't it's sort of independent of the size of the fiber, right? So these are just properties of pure glass, which is what the coherent cladding are made out of. How you control? So you can control, of course, the size, right? The size of the core, the diameter of the core, but the loss is sort of independent of that to large extent, right? This is just coming from the material, right? So I mean, we'll discuss about optical modes and how light travels in fibers and waveguides. So there we'll see how changing the core size, or for example, the refractive index of the coherent cladding, what properties it actually changes, and what it changes fundamentally is sort of the modes which are supported and what is known as dispersion. But the loss is independent of those things because it just depends on, as I said, the material, which is glass. So it doesn't depend on the structure.
So does it depend on refractive index?
No, not really. I mean, of course, as I said, if you go to a different material, then like your absorption characteristics change. But if you're just looking at optical fibers made out of glass, then how they change the refractive index is doping it by small amounts, right? So they dope the silica with, let's say, boron or phosphorus or some atoms which are maximum like a few percent doping, right? So the refractive index typically varies between, let's say, 1.45 to 1.55. Okay. So the range of variation is not much. Like how much you can vary the refractive index is not much. So it doesn't change the fundamental properties of glass. So the loss is sort of independent of that. Okay. So how the what the refractive index profile and the size of the core, etc., what they influence is what is known as dispersion, which we'll discuss next. Right. So what we are talking about is, so let's consider. So what we'll be looking at are ray paths, which give rise to what is known as intermodal dispersion. Right. So again, let's say you take a fiber or a slab waveguide. You have a core region, right, with refractive index N1 and then cladding of N2. So again, let's say the propagation direction is Z, and basically if you launch a ray here, right, so we are considering a step index fiber or waveguide for now, right? So if this coordinate is a Cartesian coordinate like X, then this is a slab waveguide. If this is R, then the radial coordinate, then it's a fiber. So N1 and N2. So this is the radius of the core. Right, so you can, as we discussed last time, so there's a cone of light here, right? Where the limit is decided by the ray which makes an angle theta c. Yeah.
Board is not seen, sir.
Sorry.
Board is not seen. Your video.
It went back. Feedback?
Yes, sir.
Yeah. Right, so recall last time we said all the rays which are within this cone will get guided because the angle of incidence at the interface for them will be more than the critical angle. So the ray which makes the maximum angle is the one which has critical angle here. Right? And all other rays will make smaller angles with the axis, right? So for example, you could have a ray which is along the axis like here, just going straight, Right, so you can now see all these rays are traveling. So let's say you have a total length L here. All these rays are traveling different distances, right? So the one which is traveling straight through, that is traveling a length L, right? But as I increase the angle, right, because they are going at an angle, they travel more distance, right? So the maximum distance is traveled by the extremal ray here, right, which makes an angle theta c here, right? So what? Okay, so because different rays are traveling different paths, and the speed at which this ray is moving is basically the speed of light, right, which is c over n1, right? So the core has a refractive index n1. So the speed of all these rays are the same, but the distance is different, right? So this ray, which is straight through traveling the minimum distance, will arrive first here at the output, right? So let's say I send a short pulse here at the input. So this is time and this is optical power. So I send a short burst right here at my input. So now that optical power is now spread out into all these different rays, right? And this ray arrives first, right? So that fraction of optical power arrives first, but the other rays are lagging behind that, right? So if all of these travel at the same speed, then at the output also I'll just get this same pulse, right? Because the whole optical energy travels together. But now what happens is this one arrives first, and then this ray at slight angle is arriving slightly later, and the latest arrival is this one, the extremal ray, right? So there's a spread compared to the input. Okay, so this pulse spreads speed time because the energy is distributed over different rays, right? So you can think of these different rays as sort of different optical modes traveling through the medium, and each optical mode, in this ray picture is taking a different time because it travels a different length. When we go to the wave picture and we actually talk about modes, we'll see that each of these different modes actually travel at different speeds. So in the mode picture, in the wave picture, what's happening is all of them are traveling a distance L, because mode is basically some transverse cross section of electric and magnetic field profile which is traveling, right? But they all have different speeds. In the ray picture, what is happening is, like we look at them as rays which are traveling at the same speed c over n1, but they are all covering different distances. But anyway, so the net effect is this, what is known as pulse broadening or temporal dispersion. Right, so you can imagine this is a problem for optical communication, right? So if I'm doing some digital transmission of data, right, so I have ones and zeros, right, and if I want to communicate at high rates, then these bits are coming at very fast, right? So for example, if you're doing 10 gigabit per second, then the distance, like each pulse repeats after 0.1 nanoseconds or 100 picoseconds, right? So imagine now, so I send a 100 picosecond pulse, but because of this dispersion, basically the pulse broadens out, right? And depending on how much broadening it is, if you have a next bit before that, then basically the bits will interfere, right? And you'll get errors at the receiving end. Right, so this is known as intersymbol interference. So basically dispersion or temporal broadening of pulses causes intersymbol interference. So that's why you want to minimize that dispersion so that you can operate at high bit rates and low errors. Right? So this particular phenomenon is called intermodal dispersion because, as I said, so these different rays are like different modes, and the differences between the modes is causing that's why it's called intermodal dispersion. Right? There are other types of dispersion that we'll discuss later in the course. But this is sort of like the biggest one. Okay, so that's why we're discussing first. Right. So So to estimate how much broadening is occurring here, delta t, right? So we can estimate by saying what is the difference in time arrival between the ray which takes the shortest time and the longest time, right? So the shortest time, as I said, is the ray which is traveling straight through. So its distance L divided by speed is c over n1. The maximum time is taken by the ray which is going like this and reflecting off at the critical angle. Right, so what is the distance traveled by that? So if I call this some delta z, then this is a right angle triangle here, right? So you can see, so this distance is delta z over sine theta c. Right, similarly, so this distance is again delta z, and this distance is again delta z over sine theta c. Right, similarly, just this keeps repeating. So what is the total distance traveled by this ray? It's just adding up all these segments, right? So basically, so you add up all the delta c, which will add up to L, right? So the total distance will be just L over sine theta c, and then the speed is the same. Right, so the spreading of the pulse is sort of the difference in the time arrivals. So that I can write like this. Right, but we also know that the critical angle is right. So then this becomes okay. So typically this is written as, so we look at the broadening per unit length. So delta t over L, right? So that's n1 over c. And here you have n1 minus n2 by n2. That is denoted as delta. Okay. So this delta is basically normalized refractive index difference between the core and cladding. I mean, sometimes defined as this, but n1 and n2 are quite close, typically for optical fibers. So either of these is good. Okay, so this is known as dispersion, which is the broadening, the temporal broadening per unit length, right? So these are units of time per length, right? So second per meter. So again, if I take sort of a typical multi-mode fiber, right? We are considering multi-mode fibers here because we are considering ray paths and different rays. Right? That automatically means, as we discussed last time, that it's a multi-mode fiber. So typical values, so N1, let's say it's 1.5. Delta is typically 10 to the minus 2. Right, so if you plug in the values here, you get this is about 50 nanosecond per kilometer. Okay. So for a typical step index multimode fiber, the dispersion, the intermodal dispersion is about 50 nanosecond per kilometer. Which means what? That if you send a signal over 1 kilometer, the broadening that you get is 50 nanoseconds. Right? So that puts a limit on the maximum data rate I can have, right? To avoid this intersymbol interference, so the next bit has to arrive 50 nanoseconds after the first. So if you take inverse of that, that will give you the bit rate, right? So 1 over 50, so that's like 20 megabit per second, right? So already this puts a limit that if you want to transmit information over 1 kilometer, then the maximum rate you can do is 20 megabit per second, right? So that's very slow. And if you want to go into larger distances, so let's say you want to go to 10 kilometers, then you can only do 2 megabit per second, right? So you can see that this is really a killer for high-speed communication, which is what optical fibers were meant for, right? So the very first generation of optical fibers, which are made in the 70s, had this limit. So there were multi-mode fibers. The core sizes were quite big, and yeah, they were highly multimodal, and so the intermodal dispersion was what limited the data rates. Nowadays, we've gone to what are known as single-mode fibers, right? Which actually the ray picture doesn't work anymore, and moreover, it only supports one optical mode. Okay? So there is, you can think sort of only one electric magnetic field pattern which is traveling. So there is no question of time differences in time arrival because there is only one mode which is traveling. Okay? So then you really eliminate this dispersion, and we'll see that even there in single mode fibers there is some limit. You still get some pulse broadening due to some other type of dispersion, but that value is much smaller, orders of magnitude smaller than what this intermodal dispersion is. Okay, so a step index multimodal fiber or waveguide is sort of the worst, right, in terms of dispersion. So the first improvement that one can do is go to what is known as graded index from a step index. So where the core has a constant refractive index. So one other thing to note here is that, so you saw here, so there is no dependence of the size, right? The size A of the core actually doesn't show up here at all, right? Which also suggests that this is only for highly multimodal fibers. So basically, this limit occurs for when sort of like your A is much bigger than lambda, right? So A is not showing up in the final expression at all. But whereas, for example, when we go to single mode fibers and see what kind of okay, so we go to graded index. What do we mean by graded index? Firstly, is that the refractive index is a continuous function, so it's graded, right? It's not constant. So okay, so now again you have core and cladding. But now the refractive index profile is not like a step, so constant in the core and constant in the cladding, but there is like a smooth variation. Okay. Maybe it looks like that. Okay, so this n is now a continuous function of if it's a fiber, then r, or if it's a planar slab, then like Cartesian coordinate. So this is some continuous function now. Okay, so the refractive index is graded, so that's why it's called a graded index fiber or waveguide. Okay, so why would this be better, right? So we can get a sense of that already from looking at the ray paths. So now let's say I launch a ray at some angle like that, right? So in the step index, because the refractive index was constant, this was just straight line, and then until it gets reflected, straight line again, right? So straight line paths. But now your refractive index is continuously varying, right? So this means that this won't be a straight line anymore, right? So as the refractive index continuously varies, this will bend, right? And then so this will be a continuous smooth curve. So the ray paths are no longer straight lines, but so if I launch at slightly different angle, so maybe it looks like that. Okay, you still have this straight line thing, right? So along the axis. Okay, so you still have. Okay, so if I zoom into what's actually happening here, right? So if I look at, if I divide the medium into thin slices and assume sort of like the refractive index is constant in each slice, so you can see that the refractive index profile is such that the index is maximum on axis, and then it starts decreasing towards the cladding, right? So if this is the axis, then this is the maximum refractive index layer, then this is slightly lower, slightly lower, slightly lower, slightly lower. So if I have a ray like this, right, so then it will bend away from the normal, right? So let's say right now we are at incidence angle which is more less than the critical angle for this interface, then it goes into the other medium, but it bends away from the normal. So now for the next interface, the incidence angle is slightly larger, right? This keeps happening until it is sort of at some particular layer, this incidence angle is sort of the critical angle for that interface, right? Then it will come back. Right? So the continuous limit of this will be like some smooth curve like this. So the bending point, the turning point here happens where for that particular layer interface, this becomes at the critical, right? And so since this refractive index is varying continuously, right, as we make these layers thinner and thinner, the refractive index between each layer is actually smaller and smaller, right? In the continuum limit, the refractive index is varying continuously, right? So that means, so this theta c, recall, is sine inverse n2 by n1, right? So n2 is almost equal to n1. So this theta c is basically just 90 degrees, right? So when it becomes tangential, right, or becomes parallel to the axis, then it turns back. Okay, fine. So now we have continuous curves instead of straight lines, or like bent curves. But how is that? We still have different rays, right? We could have different rays traveling through the medium. So you would expect that this will also have its intermodal dispersion as bad, right? But notice what's happening here, right? So the ray with the shortest path, so let's say that straight line. Now, because the refractive index is also varying, the speed, the effective speed at which these rays are traveling is also varying, right? In the step index case, all the rays were traveling at the same speed, but because they were traveling different distances, they took different times. But here, like the shortest path here, travels at a speed c over, let's say n1, which is like the maximum of this profile, right? So n1 is maximum, which means that the speed of this guy is the slowest, right? C over n1. So n1 is the maximum refractive index. So this on-axis ray which travels the least distance also travels slowest. Now look at this other ray which is now traveling a larger distance, right? But what's happening is, as it goes away from the axis, the refractive index becomes lower, which means the speed c over n becomes higher, right? So at these points where it's away from the axis, it's actually traveling faster, right? So it's traveling a longer distance, but it's also traveling faster. So you can imagine that the time that it takes would be now more similar to this guy. Although it's traveling a longer distance, it's also traveling faster, right? So the intermodal times here would now be closer spaced as compared to step index. So that's the idea here of the graded index. So we basically make the rays which are taking longer paths travel faster, so that they take less time and a time closer to the ray traveling the shortest distance. Okay, so immediately from here you can sort of, by this argument, we can expect that graded index fibers would have lower intermodal dispersion than step index fibers. Okay. So next class we'll discuss this in a bit more mathematical detail. We'll see how to calculate these ray paths and then actually calculate what this broadening would be, and then show explicitly that how we can get a big improvement over step index.